Hi, welcome to video 4.2, where we're going to be talking about intermolecular forces and types of solids. So let's first talk about molecular polarity. What does it mean if something is polar? Well, the Earth is polar. It's got a north pole and a south pole. Polarity kind of means there's differences in one side and the other. So bond polarities arise from bonds between atoms of different electronegativities. And we know that electronegativity is the measure of an atom's ability to draw electrons towards itself. When we have more complex molecules, we must consider the possibility of molecular polarities that arise from the sums of all the different bond polarities. We have to consider the geometry of the molecule. To do this full justice to this discussion, we really need to consider the concept of vectors, the mathematical quantities that have both direction and magnitude. For example, if I'm pulling with a 10 Newton force to the left and a 10 Newton force to the right, those forces cancel each other out. If I'm pulling with a 10 Newton force in this direction and a 10 Newton force in this direction, then they become additive. So back to a little physics there. Molecules themselves can be polar. That means there's an asymmetrical distribution of the electrons due to differences in the electronegativity and or the geometry of the molecule. So let's take a look at this. If I were to bind a nitrogen with an oxygen, what we would see is that oxygen being more to the right on the periodic table, again, electronegativity increases as you go up and to the right, oxygen has a higher electronegativity, so the electrons are going to get drawn towards that oxygen. It wins the fight. Now this little delta symbol, this lowercase delta, that simply means partial. So it's not a complete charge like an ionic compound might have, but because the electrons are drawn a little bit more towards the oxygen than the nitrogen, then this bond is a polar bond. The electrons occupying this area give that a partial negative charge, and it pulls them away from the nitrogen, giving it a partial positive charge. It is a polar molecule. In this particular case, on the right, the water. Water is a bent molecule. Oxygen has a higher electronegativity than the hydrogens, so the electrons are drawn up towards the oxygen in that direction, leaving a partial negative charge near the oxygen. Now where they've been removed on the other side would end up being partially positive charge. Down here on the lower left, we've got chlorine trifluoride. The geometry of this molecule is T-shaped. Now the fluorine has a higher electronegativity, so the electrons are going to get pulled towards that bottom part of the T, giving that a partial negative charge. They'll be pulled away from this chlorine, leaving a partial positive charge on that side. Ammonia, NH3, is a trigonal pyramidal molecule. The nitrogen has the higher electronegativity, so the electrons are brought towards that nitrogen, giving the partial negative charge here. Now they're removed from the base of that pyramid, so at the bottom of that pyramid we have this partial positive charge. Again, a polar molecule. On the right here, I've got carbon bonded to sulfur and oxygen. So oxygen has the higher electronegativity. That means that the electrons, oxygen has the higher electronegativity, meaning the electrons are going to get pulled in this direction. It has a negative, partial negative charge here. They're being pulled away from the other side, which is the sulfur, so that's going to lead to a partial positive charge here. Again, you'll notice that all these molecules are lopsided. They have either different elements joined. There's no middle point where it's symmetrical. Or in this molecule here, the same idea. They are opposite on different sides. So one side has the oxygen, one side has the sulfur. These other three are lopsided due to their geometry. Unshared pairs of electrons usually cause distortion in the geometry of the molecule. Unless, of course, it ends up being symmetrical, like a linear molecule with unshared pairs being an sp3d. Something like that might be symmetrical. But those unshared pairs are going to cause a distortion most of the time, leaving that molecule lopsided, polar. So what does it look like if something's nonpolar? Well, then it has to be symmetrical. We have a symmetrical distribution of electrons around the molecule. So who wins the fight for the electrons here? Nobody. They're all equal. Who wins the fight for the electrons between these bromines? Well, they have the same electronegativity. Who wins the fight for the oxygens? For the electrons in this carbon dioxide? Well, the oxygens pull at opposite directions, as they did in the CH4 in 3 dimensions. Here's a trigonal bipyramidal sulfur hexafluoride, and obviously there is no difference in their electronegativities. So it is a nonpolar molecule. Now, obviously, all bets would be off if I were to, for example, place a fluorine here. Now that thing became lopsided, right? Now this became a polar molecule. But if I don't, then it's nice and symmetrical. It is nonpolar. We're going to talk about intermolecular forces now. What types of intermolecular forces, IM forces I call them. Now, we're really dealing with a amount of separation of charge here, okay? That's what's going to hold one molecule next to another molecule, is its ability to separate positive and negative charges so that they can attract one another. Now, we know from our previous discussions that if there's a complete transfer of electrons, I end up with one anion and one cation, completely charged. That attraction is very strong. That happens between metals and nonmetals. So this isn't technically an intermolecular force. It's an ionic force, but it's on the same principle. It's just the degree of charge separation is extreme. So ionic forces are holding ions together in ionic solids through electrostatic forces. The opposite charges attract each other. These are the strongest intermolecular forces, though, as we know, ionic compounds aren't made of molecules. Ionic forces hold many ions in a crystal lattice structure. We've talked about that, how it's interlacing positive ions surrounded by negative ions surrounded by positive ions within 3 dimensions. The next type of force we want to look at is called a dipole force. Dipole means 2 poles. There's obviously this connotation that the molecule is polar. So when we're looking at polar molecules, as we did a couple slides ago, these would show dipole forces. Polar covalent molecules are sometimes described as dipoles, meaning that the molecule has 2 poles. One end, pole of the molecule, has a partial positive charge, while the other end has a partial negative charge due to the geometry and or electronegativity differences within the molecule. These molecules will orient themselves so that the opposite charge attract principle operates effectively. So if I have a group of polar molecules all hanging out together, the positive side of one molecule can form an attraction to the negative side of its neighbor. This is what we call the dipole force, more formally called the dipole-dipole interaction. But there's an attraction here, there's an attraction here. So these molecules are holding on to one another through these dipole forces. It's not as strong as ionic because we're not talking about a completely positive and completely negative ion. We're talking about a partial positive being attracted to its neighbor's partial negative. That's the nature of the dipole force. Now there's a special type of dipole force called the hydrogen bond. It's just abnormally strong. The hydrogen bond is really a special case of dipole force. The hydrogen bond is the attractive force between the hydrogen attached to an electronegative atom of one molecule and the electronegative atom of a different molecule. The 3 electronegative atoms we're talking about are nitrogen, oxygen, and fluorine, the 3 elements with the highest electronegativities. So in other words, the hydrogen on one molecule attached to an NO or F that's attracted to the NOF of a different molecule. For example, if I look at water being a bent molecule, the hydrogen of one molecule would attract the oxygen of another. So these attractions right here are super strong dipole forces. Water being a light little molecule shouldn't really exist as a liquid at normal temperatures and pressures. It's the attraction between those that holds them together that keeps water as a liquid. Thank goodness it does. And the last force we're going to talk about is called the dispersion force. It's an induced dipole, meaning that it's not a natural dipole, but it's induced by activity. We'll explain in a second. Sometimes called London forces, not because they just happen in English, but that's happened to be the name of the person who came up with this idea. So forces between essentially nonpolar molecules are the weakest of all intermolecular forces. Temporary dipoles are formed by the shifting of electron clouds within the molecules. These temporary dipoles attract or repel the electron clouds of nearby polar molecules. The temporary dipoles may exist only for a fraction of a second, but a force of attraction also exists for that fraction of a second of the time. The strength of the induced dipole force depends on how easily the electron clouds can be distorted. Large atoms, or molecules with many electrons far removed from its nucleus, are more easily distorted, thus they can generate dispersion forces between molecules that are a little bit stronger. Let's talk about the iodine molecule. So iodine has a little sigma bond holding two different iodines together. We also know that there are many, many layers to the electron clouds of iodine. If you look at its electron configuration, there are lots and lots of layers. Now, some of these electrons that are out in the further valence part of the electron are shielded from the attractive force of the nucleus by all the other electrons. This is called the shielding effect. That means that these electrons are kind of free to wander back and forth. Now, if they happen to wander to one side a little more than the other, this side would develop a partial negative charge. It would leave behind a very partial positive charge. So if we look at a group of iodines together, if the electrons did move in this direction to form a partial negative charge over here and leave a partial positive charge on the other side, its neighbor is going to feel that negative charge and its electrons are going to be repelled away. So it is going to be induced to becoming partially negative and partially positive. Now this atom below is going to feel that partial positive charge here, and its electrons are going to be attracted to that positive charge, making a little bit of a negative charge here and leaving a partial positive charge here. And its neighbor is going to feel that partial positive and move its electrons towards that, forming a partial negative and leaving behind. You get the idea. One induction, one induced dipole, forces the others to become partially negative or partially positive. Now this is a temporary condition. It's not built into its structure, and it's not a very strong force, but you can see why it's called an induced dipole. The action of this movement right here caused the movement of everyone else to become partially polar. Interesting, huh? Again, the key to this one is that this is a non-polar molecule when we're talking about dispersion forces. Both the hydrogen bonding and the dipole forces take place with polar molecules. Hydrogen being hydrogen bonded to nitrogen, oxygen, or fluorine for that hydrogen bonding to occur. When we look at the strength of the intermolecular forces, the ionic, again, not really molecular, but that's a complete separation of charge. That would be by far the strongest bond. Hydrogen bond is less strong than that. Dipole, weaker, and dispersion being the weakest. So we can use this information to start getting trends about melting points or boiling points, because the stronger two particles have as an attraction, the more difficult it is to melt them or to boil them. So the higher the attraction, higher the melting point. So we can answer questions like this. Who has a higher melting point between sodium chloride or C2H6, it's called ethane? Well, I know this one is ionic. This one is a molecular compound. It's two nonmetals. So without a doubt, I know this one has a higher melting point because it's ionic. This second one, they're both molecular, but a quick Lewis structure would tell you that the sulfur dioxide is bent. The carbon dioxide is linear. This guy is non-polar, whereas the sulfur dioxide is polar. And again, what that means is this is going to form a dispersion force. This one is going to form a dipole force. This guy has a built-in polarity, therefore SO2 is going to be the stronger of those two. The dipole is greater than the dispersion. For this third choice, well, chlorine, Cl bonded to Cl, has to be nonpolar. Hydrogen bonded to fluorine is a hydrogen bond because hydrogen is bonded to either nitrogen, oxygen, or fluorine. Those are the three special elements for hydrogen bonding to occur. So I know that this one has to be higher because of hydrogen bonding is going to be greater than that dispersion force formed by chlorine. These ion forces also tend to increase with molecular mass. So we know where the mass number is on the periodic table. If we add all the masses up for a molecule, we get what's called its molecular mass. Now, the higher the mass is, the more it's able to polarize its electrons, the greater attraction it's going to have for one another. So who has a higher melting point between fluorine and chlorine? Well, looking at the periodic table, chlorine is a bigger molecule, has a higher mass, so it would have a higher melting point. Who has a higher melting point between C5H12 or C3H8? Now, obviously, this one is the bigger molecule. So when things are the same, then we look at the mass to determine, okay, which one has a higher melting point or boiling point. The last thing we're going to talk about are the different types of solids. The first one being molecular solids. We know molecular solids are made up of atoms or molecules held together by London dispersion forces, dipole-dipole forces, or hydrogen bonds. Those are fairly weak. Again, it's partial positive, attracted to its neighbors, partial negative, not very strong. Therefore, these things tend to have low melting points. Think like wax. Think about like tar. Think about air itself has already melted and boiled away at this temperature. Very low melting points. They are poor conductors of electricity and heat. The electrons are trapped in their covalent bonds. We know electricity is the movement of those electrons. So if they're trapped in there, they don't conduct electricity very well. Molecular solids don't conduct electricity all that well. Things like water, sugar, wood, oxygen, the nitrogen in the air, plastic, a lot of our world we see are molecular solids. Next one we'll talk about are ionic solids. We know these are made up of positive and negative ions held together by that electrostatic attraction. That attraction is very high. So they're held together very tightly. They have very high melting points. Don't try to melt salt on your stove. You'll be very frustrated. You can melt sugar very easily because it's molecular. Don't try salt, sodium chloride. You'll just burn your pan up. They're brittle, and they're poor conductors in the solid state, meaning all the electrons are locked into their ions when it's solid. But if you dissolve them in solution or you melt them down, then they start to conduct electricity. And that's why water itself, I mentioned, is molecular. It does not conduct electricity. But if you drop a hairdryer in a bathtub, that's a terrible thing. Why? It's the salt in the water that's conducting the electricity. That make sense? Examples of some ionic solids: salt, we just mentioned, baking soda, which is sodium bicarbonate, Epsom salts, which is magnesium sulfate, or milk of magnesia, which is magnesium hydroxide. So a lot of the ionic substances we see are in their solid crystalline form, or they are in aqueous form, dissolved in water. Metallic solids are made up of metal atoms that are held together by metallic bonds, which is based on this thing we'll talk about called the electron C model. There's a wide range of melting points. For example, mercury is a liquid at room temperature, but some of them don't melt for thousands of degrees Celsius. Most of them are pretty high in terms of metallic solids. They range from soft and malleable to being very hard, and they are good conductors of electricity because their electrons are free to roam. So the idea is we know that molecular materials do not like their valence electrons. So let's just focus on this little nucleus here. It can give up its valence electron to the group. Now it sort of is acting as a positive charge because it's lost its electron, but the electron's just floating around out there. It's not really belonging to anybody. Now, it's like a game of hot potato. This atom here is also giving up its electron, so it's positively charged. But the electron's out here making a negative charge somewhere, so it's attracted to that group, but no one really owns their valence electrons. It's called the electron C model. So things we're familiar with that are metallic, a lot of our world's metallic as well. Steel, gold, platinum, brass, things that you know that are metallic. My favorite of this category are the network covalent substances. So they're made out of atoms that are covalently bonded to all their neighbors. The intermolecular forces are covalent bonds as well, meaning that the carbon is bonded to every other carbon within, for example, a diamond. So in this lower left diagram, you can see that each carbon is covalently bonded to the next carbon, which is covalently bonded to its neighbor, etc., etc. So it's a three-dimensional array of covalent bonds acting as one giant molecule. Well, some things that we know of that are network covalent solids are very hard. They also have very high melting points. I don't even think you can melt them. They would be so hot by the time they separated from their group, they'd probably vaporize. And they are very poor conductors. Very hard, high melting point, poor conductors. Some examples of network covalent solids. Diamonds, which is an allotrope of carbon, meaning it's a way that carbon can bond. Silicon carbide, that is something they use on drill bits and then sandpaper. Silicon dioxide, which is quartz, they also use that in sandpaper a lot. They're not all that common, but they're extremely hard, high melting point, very difficult to break apart. Well, they're hard substances we know of. And so that pretty much does it for our lecture on intermolecular forces and types of solids. Thank you very much.